For example 2, we are going to write an equation of a tangent line. And we've done that. Equations of tangent lines. Tangent lines are going to be straight lines, so we're looking for y equals mx plus b. We've got to find the m, and we've got to find the b. And what we'll do is look at the function. It's going to be some kind of curve, and we want to find the equation of a tangent line at the point -1, 1. So we already have the point. The point is going to help us find b. What we need is the slope. So to start, we'll find the slope by finding the derivative and plugging in x equals -1. So we'll plug in -1 for x once we get to that point. So here we go. We're going to have to do the derivative of this function. This function is it's pretty complicated because it has a fraction within a fraction, and so it is a quotient rule because it's a fraction. But this fraction within a fraction is really going to kind of mess us up. So I think the first thing that I'm going to do in order to make this simpler, you'd have a couple options. The first option would be to just move that x to the -1, or x to the 1 to the top of this little fraction to make it x. Can you see that? X to the -1, just do that. Or I'm going to do a little trick instead that I like better, and I'm just going to multiply everything by x. I'll show you how that works. If you have a function, excuse me, so I just copied that function a little bit bigger. If you have a function and you want to multiply everything by the same thing, like x over x, or you could do 2 over 2 or 3 over 3, as long as you do the same thing on the top and the bottom and you multiply that x by every single term, you're not going to change anything because you're multiplying by 1, and it's going to make it hopefully simpler. The reason that I picked it is when I distribute there, I get 3x. When I distribute here, I get 1x times x. My x's cancel, and I just get a -1. So I picked the denominator of that fraction within a fraction, multiplied that by every term, and now I have this function, which I think I can find the derivative of easier than the original one, because the original one had a fraction within a fraction. So now I'm going to do this. The top is my u, the bottom is my v, and I'm going to use the quotient rule to find the derivative of this because it is a quotient. There's an x on the top, there are x's on the bottom. It requires the quotient rule to find the derivative. All right, so here we go. The quotient rule is v, so I'll copy v, times the derivative of x, the derivative of u, which is 3, minus u times the derivative of v, all over v squared. Because I'm doing equation of a tangent line, I need a slope. I could spend some time simplifying this and then plug in -1, or I can just plug in -1 right now. I'm not going to spend any time simplifying because I don't need to end up showing a derivative. I just need a slope. So I'm just going to plug in -1. I'm going to do a little bit of work in my head. -1 squared is 1. 5 times -1 makes that -5 times 3. 3 times -1 is -3 minus 1. 2 times -1 makes that -2 plus 5. -1 squared is 1 plus 5 times -1 is -5 squared. I just got some work to do. So 1 minus 5 is -4. -4 times 3 is -12. And then this set of parentheses is -4. This set of parentheses is 3. So that ends up being negative 12. On the bottom I have 16, and on the top I end up with 0. So my slope, after all that work, is 0. So now I have a point. My point is negative 1, 1. I have a slope, so I'm going to use point-slope form to write my equation of a tangent line. Y minus the y coordinate equals 0, x minus the x coordinate, and I end up with y equals 1.